the first speaker of today, it's me, Jordi Blasco. And I'm going to talk about the work that we have done, Jose, my colleague, and myself, in order to try to converge the AI, the new wave of AI need into an HPC kind of a solution. So over the last few years, we have seen a lot of demand of a new wave of AI users that they require kind of a very different kind of setup. Okay, so as a HPC consulting company, we see this growing demand happening every day more often. The situation is it's quite complex at this stage. Why that? Because so while most of the HPC users, most of our clients, they are using AI already, and they have a pretty well solid HPC background. Transiting from HPC to AI, it's only the same thing. So they just use a different kind of application. Okay, rather than using molecular dynamics or fluid dynamics, they are using TensorFlow or similar things. They just use different set of applications installed in a HPC cluster. But what is happening with these new people that are coming from an AI background, and they are transiting really from a laptop-oriented compute solution to something that they need to scale. And this is the situation now. So we have seen that there is no transition between one and the other, and that's why they are demanding something that should be easier for them. And it's not just AI. So it's important to point it out. So there are a lot of new researchers coming that they demand something a lot easier. They don't have experience in high-performance computing, and that's why we see a lot of more interest in things like open on demand and so on. Okay, so this new emerging reality. It's creating a bit of drama on several supercomputing facilities because the software stack requested it's slightly different, and to combine both of them, both worlds require a little bit of effort. So the talk that we have today, it's targeting this kind of need. Okay. Okay. So one of the main tools that we see this new community requesting is Kubernetes. Why Kubernetes? Kubernetes, it's a widely used technology. It's really well supported and understood technology in IT, generic IT, okay? But now incorporating this in a more compute-friendly is when we are starting to see challenges, okay? So at the end of the day, what is good from Kubernetes is that it comes with the application portability out of the box. So because all the applications that AI users are using are coming either from Docker Hub or from NVIDIA repository, you download the Docker image and you get into a pod and you can start to run, okay? And that's good because it comes with a zero effort from the AI user installing really complex applications manually. So it's a lot easier for them. And then in addition to that, there are new graphical user interface applications that they interact directly with Kubernetes, and you can run your workflows embedded in a Kubernetes environment. So I'm talking about Kubeflow, and I'm talking about Nextflow, I'm talking about many other applications like that. Okay. But so these important things here, and this is a concern that I would like to raise here, and probably you are very aware about that. If you do this way, and if you provide something like this, the risk of underusing the platform, the risk of running something that it's not fit for performance or efficiency, it's really, really extremely high, okay? And having said that, and so the people that coming from HPC background, they see this on a daily basis, okay? And believe it or not, the community that comes from AI, they're still asking for it. The main concern is not about the performance or the efficiency. It's more about the availability, about getting started too. Building up this awareness of how to use the platform accordingly and as expected, it's something that we need to work with them, to raise this awareness. Okay, rather than waiting for 10 days, you can get the results back in less than 1 day. Rather than spending 10 millions on the cloud, maybe you can spend 10 times less. Okay, so I'm going to talk about this later. Okay, but the reality is this. So this is a survey conducted by SIG HPC on the top 500 sites, and we understand really well all the tendencies that we have there, all the traditional HPC workload managers and resource managers, right? So Slurm, not a surprise, it's the one dominating the top 500, and then we have the long tail of LSF, Maui, Moab, and so on. But have a look at this. Kubernetes, it represents at 10%. It's the second, I would say, resource manager in the top 500, okay? So the reality is this, okay? And it's going to be here to stay. And not a surprise that NVIDIA ended up buying Run AI. And this is a news that I think it was 26th of April, so pretty new one, and highlighted the importance of Kubernetes for running AI workloads. It's not yet ready, but we do it anyway, okay? So the objective of this talk, the objective of the work that we have done here is to try to move Kubernetes to a point that we can do more and we can run things more efficiently. So the main concerns that we have, it's obviously efficiency and performance. The Kubernetes, the way it is, the way you can set it up coming from the manual, it's not enough for leveraging the response for AI at the scale. So something else needs to happen. You need HPC-alike technology in order to be able to meet those demands. And I'm talking about PMIX, and talking about the CPU binding, and talking about memory affinity. So the NUMA domain kind of fine grain and backfilling preemption. So it's not yet there. Okay, so it's something we are working, and there are a lot of people working towards this, but it's not mature enough to compete with something like, for example, Slurm or LSF. And at the end of the day, so this significant performance and efficiency have an impact on the finance, has an impact on the service delivery, and on the scientific output as well. So how we can address those needs in a way that we can use the HPC kind of solutions that we have. How we can satisfy those demands of this emerging new community, but also providing this kind of building up this awareness about performance and efficiency, and what is expected what we should expect in the future. Okay, so this is basically what we are going to do. So the first topic is Kubernetes over Warewulf. So I suspect that all of you know already Warewulf, so there is not too much introduction needed in here. But for those that probably are watching at the other side, if you are coming from an AI background, Warewulf is one of the most popular cluster managers in the HPC world. So it allows you to provision a cluster, very large scale cluster with a stateless provisioning. So you only need an image, and this image will put on every single compute node, and you can have thousands or tens of thousands of them. So this makes the cluster administration a lot easier, because you only need to worry about one single image for the same set of compute nodes. If you have maybe GPU nodes, you are going to have another image for that set of GPU nodes. Okay, and this also plays with economics of the whole setup, because having a stateless provisioning, there's not that much requirement for local file system. So you're going to use a very powerful cluster file system to run AI or HPC models. Okay. And so the approach that we have is basically making Slurm and Kubernetes to coexist in the same compute nodes. So what we are going to have is front-end kind of applications like Open on Demand or Kubeflow or any other AI dashboards, SSH for traditional HPC users or advanced HPC users, and they are going to communicate with Kubernetes or Slurm. So we are going to have both daemons at the same time in the compute nodes. The only difference is that automatically managed by Slurm, we are going to take advantage of the power-aware scheduling that comes natively from Slurm to reduce the number of nodes available in Slurm in order to have more nodes available in Kubernetes, or the other way around. If we need more Kubernetes nodes, then we are going to reduce the number of nodes in Slurm. And in order to achieve this, we need obviously CSI to expose different cluster file systems, and for the Slurm, we are going to have native cluster file system client. So this is still important also for the AI new AI people. So AI IO, it represents a extremely high percentage of the workload. If you don't use a really powerful cluster file system, the workload will be affected as well. So it's important to have everything aligned in a way that works just fine. So this is a strategy, okay? So using basically the scripts that we call every time we see less demand on Slurm. So we are going to do an S-control update, node name, and the nodes that we want to suspend or to drain, and we are going to place the reason, like those nodes are going to be moved to be repurposed for Kubernetes. And then from the Kubernetes side, this is happening on the same script, okay? We are going to do kubectl and cordon and then the node. So this way we are taking away one node from Slurm, and we are enabling it from Kubernetes. And if happens to be the opposite way, we are going to drain the node from the Kubernetes side, and we are going to resume that node from Slurm. So this is something that we have done for other clients already. Back in the time for IRB as well, when they had Docker Swarm and EdgeCat, I believe. So it's something we are used to, and it's pretty easy to integrate this. So it's just a matter of incorporating a bit of a custom development for this. Okay. So the other important component here around performance and portability is exposing really high performance applications. And the solution doesn't come from the container point of view. This is from our view, okay? Containers and conda environments and RPMs are meant to be used for portability, not that much for performance, okay? So there's a lot of work going on the container side for HPC. We have some talks that we are going to see today, but the way that you are going to use it, if you download something from the Docker Hub or from other places, you are going to see that it's meant to be used for portability. You can run it anywhere, okay? So when you do that, you lose a lot of performance. You build this with a zero level of optimization to achieve this portability. With Easy, we are able to build a software ecosystem that's highly tuned for every single hardware microarchitecture. So this way, we're exposing really high performance applications, binaries and libraries and so on, that really matches the performance that you get. So it's not about reproducibility and portability, but also performance reproducibility, which is quite a key topic. So Easy, it's a collaboration between different European partners, including HPCNow. And so the goal is to build a scientific software that it's shared across the globe. So as a main requirements, it's reproducibility, portability, and performance. And has been inspired quite a lot from the Compute Canada software stack. So why this gap in terms of performance? So when we talk about this with scientists and engineers, we say, so this is with Haswell, okay? So it's a previous generation. We are now here in Skylake, okay? Skylake microarchitecture. So this gap between here and here, it's more than 7 times speed up. So when we talk to scientists, we say, look, rather than waiting for 1 week, you wait for less than 1 day and you get the results right away. So that's awesome. So we have convinced the scientist. So it's a no-brainer. I'm going to use this. When we speak to finance, how much you pay for cloud expense? So how much you pay in cloud, or how big it needs to be your cluster? Okay, so you can go to 10 times smaller, either the bill or the platform that you need to procure, right? So what's the magic around this? So that's the completion flags that you are using. So if we are not exposing AVX into an other micro-restriction sets in the build time, we are losing those hardware capabilities. Okay. So we are treating basically architecture like it was back in 2008. And 2008, we were able to generate, so the platform there was able to deliver 4 floating point operations per cycle. Nowadays, we have 32, okay? So it's quite a big gap. Next year, with Diamond Rapids, it's going to be double that bad. So it's going to be 64 versus 4, okay? There are additional things other than AVX, but AVX is the one that is dominating the floats per cycle. And this is, it's extremely important, this is for double precision. AI uses single precision or half precision sometimes, so you can multiply this by this factor as well. Extremely important here. So the easy architecture relies on many things, okay? So basically, we have easy build on top of ArcSpec and LMOD to build a scientific software in automated and reproducible way. So by the way, this easy architecture will work in the same way if we replace easy build with SPAC, okay? Which is the equivalent of easy build, but in a different setup. Then for compatibility layer, we are using Gen 2 prefix. Gen 2 prefix makes the software completely agnostic from the OS distribution. So if you are using containers for code portability, Gen 2 prefix makes containers completely obsolete. There's no longer need for containers in this for this kind of a scenario. And then with Slurm BMFS, we are able to expose some file system into Slurm BMFS, and Slurm BMFS has an architecture that allows you to distribute this information, replicate this information on multiple tiers. And so I'm going to speed up this a little bit. So we save every single byte we save in the stratum 0, it gets automatically replicated in the other tiers, and then those tiers offer the same information through a proxy. So this is happening using HTTP protocol. It's read-only, and it's extremely fast. So it's perfect for this kind of a scenario. So compare this to AI based on a Kubernetes. You need to download a container, or you need to download your binaries. In this kind of a scenario, you only need to mount this. You don't need to do data staging before you run something. It's already there. Okay. So how we integrate this into Kubernetes? So using CSI in the same way. So there's a plugin that allows you to mount this, and this is how it looks like. So this is a recent work that we did for a really big pharma industry. And then you are interacting in the same way that you usually interact in an HPC environment. So you load the modules, and you use the applications that you have there. Okay, so what else is missing? The batch system. So there are few options already available there. Okay. So at the time we did this exercise, we evaluated Flux framework, we evaluated a Q, and we evaluated Volcano. And we finally went for Q because we had to pick up one. And we used this one because it was already integrated inside the Kubernetes core. And before we move to the next, before I move to the next slide, I have to mention that there is a lot of people working currently towards a situation where we can get a batch scheduler in Kubernetes able to do what we can do with workload managers like Slurm. Okay, and there are a lot of approaches here. So there are people that they say, getting this to be able to do what Slurm is doing, it will take a lot of effort. So let's try to make Slurm to work with Kubernetes. So there's a lot of things going on, different approaches. Okay, so at this stage, what we have is this batch queue system that is only able to review the resources that are available and allocate the jobs in there. So there's no backfilling. There's a lot of features that are missing there. I'm going to skip those slides because I'm running a bit of out of time. But you're going to have those things available in the website. Okay, so that's pretty much it. So just one more visit. So the next step about what is coming, KCP, it's going to be disruptive technology that we think will be able to bring both worlds closer. Basically, because KCP it's a podless and containerless Kubernetes environment. So it feels like a Kubernetes, but it's not strictly a complete Kubernetes. And we have a couple of talks today that will talk about different approaches to get this integrated into a more HPC-alike. So one is from Carlos Arango, and another one is from Vanessa Sochat. So I'm going to stop here. Thank you so much.